So our third speaker is Yuxiang Wang, who's an assistant professor in the Department of Computer Science here at UIUC. He is also affiliated with NCSA. His work is in computer vision, machine learning, and robotics. He has a particular focus on few-shot learning, meta learning, open world learning, streaming perception, and generative modeling. He did his PhD and a postdoc at CMU in robotics. He's received several awards, including Best Paper Honorable Mention for Streaming Perception in ECCV, Best Paper Award finalist in CVPR. He's been recognized as a notable area chair in ICLR and an expert reviewer in TMLR. So he's received several other awards as well, Amazon Faculty Research Award, and we're very glad to have him with us for our third speaker. And hold your questions until the end. Thank you.
Thanks, Tandy, for the introduction, and good morning, everyone. It is my great pleasure to be here. I'm sorry that I cannot join in person. My name is Yuxiang Wang from UIUC. So there have been a lot of insightful talks on generative AI. I will talk about some efforts towards unifying generative AI and discriminative AI in the context of the open world. As we know, generative AI has emerged as a new way following discriminative AI. The community has developed various types of powerful generative models, such as language model, LM, diffusion model, neural ratings fields, and NERF, to name a few. They are able to create impressive text, code, images, and even videos. But creating alone isn't the ultimate goal. What we need is to understand and take action in the world through the generation process. So, what is missing when integrating generative AI in the physical world? First, our world is 3D plus time. Only synthesizing 2D images is not enough. The generation should be rooted in 3D and even 4D. Second, our world is open and dynamic, where never before seen objects, concepts, and scenarios are continually emerging. So the generative models should be able to simulate unseen variation of the world. Third, we need to bridge generative models and discriminative models so that they cooperate with each other and improve the performance and downstream tasks. In this talk, I will mainly use generative models developed in computer vision as an example, with some additional example from ML as well, and discuss some of our group's work on unifying generative and discriminative AI in the 4D open world. To this end, we first need to advance generative models to perform generation in the 4D physical world. The first step is to lift successful 2D image generation models like diffusion models to synthesize objects or things in 3D and 4D. Greg just talked about this, and Shenlong also mentioned this. Not only do we want to accurately reconstruct the 3D object or things, but we also would like to manipulate the generative models through language-based instruction to edit the object or things as illustrated here. Unlike 2D image generation, the foundational difficulty here is the lack of 3D training data. That means, so far, we still don't have a generalizable 3D diffusion model. As illustrated here, current 3D diffusion can only generate simple 3D objects from specific classes. So the widely adopted solution is to distill the 3D generation or edit signal from pre-trained generalizable 2D diffusion models, such as using score distillation sampling proposed in Dream Fusion. The basic pipeline, such as in instruct NERF to NERF, is formulated as follows. NERF is first trained on the original images to reconstruct the object in 3D. And then a diffusion model like instruct pix to pix is used to edit the images in 2D with the language-based instruction. And then nerve is tuned to reconstruct the added object in 3D from these generated images. So we can render the added object in 3D. So we have been talking about nerve in previous talks. I assume most of you are familiar with nerve, neural readings field. Here is a brief background on nerve, since nerve is one of the key techniques we leverage here. As a widely used 3D representation, nerve is able to render novel views of a captured scene based on a given set of input views. Nerve represents a scene with color and density fields modeled as a 5D function with an MLP f theta. The input is 3D location X and viewing direction D, and the output is the color C and the volume density sigma. And the volume rendering is performed by sampling points on the ray and querying the MLP f theta. The MLP is learned by comparing renderings with ground truth. While nerve tries to produce 3D consistent reconstruction from the given images, the 2D diffusion model cannot provide multi-view consistent images during the editing process for nerve to operate. This becomes one of the major challenges of this widely adopted solution. We have developed a series of work to overcome this issue, which generates high-resolution, 3D consistent editing or style transfer result in complicated things. Notably, a common failure case, checker jacket in prior work, has been successfully addressed by our model. So the key insight underlying these approaches is to not solely rely on nerve, but explicitly propagate the editing information across different views, so to ensure multi-view consistency. And here I will mainly focus on one approach, VicaNerve, which introduces two sources of regularization to explicitly propagate the editing information across different views. The first one is a geometric regularization. Given that nerve produces depth information for free, we leverage it as a guidance to establish image correspondence between different views. So we first added several key views through instruct pix to pix. These key views are sequentially sampled to have a reasonable overlap with each other. Meanwhile, we extract the depth information for all images through nerve density. Using the rough depth estimation and camera poses, we warp and project added key views to other views of the original frames to maintain 3D consistency. This leads to a mix-up data set. However, only this mix-up step is not enough, because the depth estimation from nerve can often be noisy, leading to certain incorrect correspondences. To this end, we further introduce a learned regularization. So the key idea is to design a blending module that aligns the latent codes in the 2D diffusion model between added and unadded images. So this leads to an updated data set with more view consistent and homogeneous images. After that, we use updated data set to train the nerve. So in addition to significantly improve the multi-view consistency, our approach is also much faster than previous method. For example, 3 times faster than instruct nerve to nerve. This is because of the decoupling of the diffusion process and nerve training, which is basically an iterative procedure in instruct nerve to nerve. Since nerve tuning takes most of the time, further speed up can be achieved with a more efficient nerve backbone. Our approach also achieves kind of appealing controllability so that we can control the final result at an early stage of editing by editing key views. Because of this improvement, our approach can work with a broader range of instructions. So here is an example. Turn him into a robot is one example where instruct nerve to nerve fails, but we succeed. And these quantitative comparisons show that our approach improves editing details and the overall style consistency compared with the state-of-art instruct nerve to nerve. So here are some kind of more challenging scenarios, right? We can see that instruct nerve to nerve encounters several issues. such as insufficient added like the robot bear, noisy added like the Spider-Man, and even incorrect added like the fair work. By contrast, our approach achieves a significantly better result in these scenarios. We conduct comprehensive quantitative evaluation under two metrics. So here, the text-to-image directness score measures the feature similarity between the edited rendering and the text instruction. And the consistency score represents the consistency between different frames. So for both metrics, the higher is better. We can see that our approach consistently achieves a higher performance. Notably, as the edits becomes more challenging, we can achieve significantly better scores on both metrics. We further extend this success from 3D to 4D, therefore achieving style or object-specific editing of challenging 4D dynamic scenes. In addition to style editing, we would also like to edit the 3D shape of the thing. This is a bit difficult for NERF, since it is an implicit scene representation that doesn't support shape editing. On the other hand, explicit representation like point cloud natively allows shape editing. So intuitively, NERF rendering can be interpreted as porting a point cloud. So we integrate NERF and point clouds to benefit from both of them, leading to point cloud guided NERF. More precisely, we propose a neural editor and improved point cloud guided NERF that supports human guided shape editing by directly manipulating the point cloud. To fulfill our task of shape editing, our improved point cloud guided NERF is based on early work of point NERF. But we make 4 major advancements to support shape editing, including point cloud organization, rendering scheme, shape optimization, and color modeling. With this improvement, we are able to propose a unified framework for general shape editing tasks. So NERF requires a data structure to skip empty space and focus on crucial parts. So point NERF uses a single scale method to construct bounding boxes. As an improvement, we use KD tree to produce multi-scale bounding boxes or voxels. Each layer represents a scale, making the top-down process of a tree a native coarse-to-fine approximation of the shape. So we then render over the KD tree guided voxels by only sampling points in voxels at a layer through a top-down recursion. So as such rendering schemes guarantees the complexity upper bound of each voxel, we propose a deterministic spline integration rendering scheme inspired by our earlier work of Diver. So we first uniformly sample points on the intersecting segment, calculating their embeddings, and then perform a spline integration to calculate the average embedding as the embedding of a represented sampled point in the rendering formula. Such deterministic scheme is efficient and stable without random sampling and accounts for the embedding of the whole segment. So we also model surface normals for better shape utilization. So there are 2 ways to calculate the norm, basically. One is to estimate from nearest neighbors of point, or calculate by the gradient of the volume density of the NERF. So we regularize these 2 estimations to be the same, to prove the outliers with abnormal norms. So by engaging the norms within the training process, we provide more clues of optimizing the shape and potentially lead to a precise point cloud. And then we further utilize the norms for color modeling by using the font reflection. Observing that specular is kind of function of reflection of viewing direction by norm, we model view-dependent color as a function of such reflection. We also model other attributes like reflection and shininess constant to achieve better color modeling and decomposition and norm utilization, basically. With the improved point cloud guided nerve, we define the unifying shape editing with an indexed point cloud. So we define a point cloud being a mapping from index to point. And the scene editing operation is basically another point cloud of the same set of indices. This means that a point of the index moved to the new location, basically. Such definition is general with minimal information, without any assumption of smoothness, continuity, or types of models. But it covers the shape deformation task and also the more challenging shape scene morphing task, which has not been studied by previous work. So we apply such a scene editing on our improved nerve by directly replacing the point cloud. So the edited nerve is still valid and full functional. This means it can support fine-tuning. On the quantitative benchmark constructed by us, our neural editor significantly outperformed baselines in shape deformation and further improved consistency after fine-tuning. So the quantitative result also show that neural editor renders a more realistic result than the baseline point nerve in shape deformation. More noticeably, our neural editor also enables more challenging scene morphing tasks, which is not supported by previous work. And the neural editor renders much better than point nerve. So we can see that point nerve's result contains some blur texture, shadows, and gloomy and non-smooth color. By contrast, our neural editor renders results with clean texture and bright colors. So the ablation study shows that all of our design choices, including the deterministic spline integration rendering scheme, the surface normal for shape utilization, and the font reflection color modeling benefit our rendering result. While removing any of them clear still kind of outperforms the point nerve. So some of the designs don't show a high improvement in zero-shot inference. But in the fine-tuned scenarios, right, so the performance severely drops after removing that. This shows that these designs also benefit the fast fitting towards consistency. More broadly, we are able to synthesize not only RGB images, but also a variety of the scene properties simultaneously, including semantic labels, surface normal, shading, edge, and key point, which are crucial to 3D scene understanding. We achieve this by first showing that nerve is able to render a specific scene property by extending the MLP to output the scene property in addition to color. Then we learn how to render these scene properties simultaneously by modeling their relationship. To this end, we introduce a new task, multitask view synthesis, where we reformulate multitask learning as a set of view synthesizer problems. While multitask learning has been widely investigated in the context of discriminative models, our work is the first that introduces multitask modeling for generative models. Compared with the conventional multitask discriminative learning, which overlooks 3D constraints such as multi-view consistency, our reformulation enables the whole system to leverage both cross-view constraint and multi-view synergy for scene understanding. This is exemplified by our movie nerve model. So the model first processes multi-view features with the cross-view attention module, aggregating the information from different views to refine the features. Then a cross-task attention module utilizes multitask synergy to enable knowledge sharing across different tasks. Finally, with the decoded weights for aggregating scene properties, the model performs a weighted sum to obtain the multitask prediction of the novel view. Again, here the key benefit is that MUVI-NERF leverages both multitask and cross-view information, while conventional discriminative multitask model can only model the multitask relationship. Due to this multi-view consistency and the 3D awareness of our generative model, it significantly outperforms the state-of-the-art discriminative multitask model, which produces noisy and kind of inconsistent results. And here is a more comprehensive quantitative comparisons. So to extend the discriminative model to solve this kind of multitask view synthesized task, we first use NERF to render novel view RGB images, and then apply discriminative multitask learning models on generated images. Here we use GeoNERF, a variant of a conditional NERF. So we train the model under 3 data settings. The first is train on ground truth RGB and same property annotation pairs. Second is the first train on ground truth RGB and same property annotation pairs, and then fine tune on synthetic RGB. And third is to train on ground truth RGB and the same property annotation pairs, and test on ground truth RGB, which is basically the performance upper bound of the discriminative model. Our approach consistently outperforms the discriminative model in different data settings. Notably, MUVI-NERF provides kind of a universal benefit for different conditional NERF encoders, such as Pixel NERF, GNT, and MVS NERF. We also observe that the multitask and cross-view information learned during the training actually benefits RGB synthesized in out-of-distribution data set. This is illustrated on the blended MVS and Tata error. Okay, so far, we have introduced this kind of geometry awareness into generative models when extending them to the 4D world. Another important property is that the generative models should be also aware of physics when integrated into the physical world. While this can be achieved by considering physics simulator, for example, our recent work shows a simpler strategy in the context of diffusion models for the task of the 3D human-object interaction synthesis and prediction. Given past sequences of human-object interactions illustrated by green meshes, our approach predicts and synthesizes plausible future sequences showing colored meshes. So here, physics means that there should be no penetration between the synthesized human body and objects, and their content should be modeled correctly. Our method stems from actually a simple yet important observation. While the overall human-object interaction might appear complex, the motion of an object relative to its contact point often shows a straightforward and predictable pattern. So this shows some kind of examples. Basically, for the motion clips on the behavior data set, the relative motion on the right might revolve around the steady axis or just remain almost static. So drawing inspiration from this observation, the key is to integrate coordinate transformations into our generative model that synthesize the interactions. So specifically, we introduce an interaction correction step designed to adjust the object's motion based on the contact references. Here is how it works. Given a human-object interaction sequence derived from any generative model, right, which might contain some anomalies such as contact penetration, we find that the coarse contact information can be inferred from geometric cues, though the interaction sequence is not perfect. And then a reference system can be determined using this contact information. With this reference in place, we train a network to correct the relative object motion and prompt the interaction plausibility. The resulting predicted motion is then reprocessed through a reverse coordinate transformation, preparing for the next phase. So in our approach, we embed this kind of interaction correlation step into every iteration of this kind of interaction diffusion. So here, the interaction diffusion is basically a generator built upon the DDPM, the noise and diffusion probabilistic model. As shown in the right figure, we employ a transformer-based encoder-decoder architecture for the parameterized reverse diffusion, which is tailored to map past motions and object geometry to their denoise future interactions. And the left figure shows our process. So first, during each cycle, we derive a denoising interaction sequence from the reverse diffusion process. And then a correlation scheduler evaluates the sequence to determine if any refinements are required. If corrections are deemed necessary, we then use the interaction predictor to correct the object motion with the contact reference inferred. And finally, reiterate the correction into the forward diffusion. So note that the diffusion and the correction are not intertwined during the training. Instead, they merge seamlessly during inference without any fine-tuning. And here are some results. We compare our proposed method interdiff with a baseline MDM on the behavior data set. So we can see that interdiff consistently outperform in terms of both human and object accuracy as well as interaction quality. Notably, compared with plain diffusion, our method outperformed by providing more enhancement over a broader sample size. Furthermore, we can observe that interdiff's ability to predict precise object motion notably boosts the accuracy of a human movement. Consistent with the quantitative result, right, we observe that our interdiff yields more plausible interaction predictions. And also compared with the ground truth motion, our method produces smoother interaction sequences, despite being trained on noisy mocap data set. Here, I would like to emphasize the ground truth is actually quite noisy and not accurate. We also conducted an ablation study that shows the efficacy of the coordinate transformation. So we can see that in the absence of the reference system transformation, the object motion integrated into the diffusion fails to align and catch up with the contact motion. This misalignment actually leads to notable artifacts, particularly in the long-term autoregressive generation. Also, this kind of interaction is not limited to humans and objects, but could be also happening between multiple persons. So in another line of work, we have also investigated stochastic multi-person 3D motion forecasting by introducing a decoupled bi-level modeling framework. So at the local level, we model motion for different people independently under some kind of relaxed conditions, so as to prompt single person fidelity and diversity. Meanwhile, at the global level, we model social interactions by considering the correlations between all motions, so we can improve further the multi-person fidelity. Okay, so far, we have discussed how we advance the capability of generative models in the 4D world. So they are geometry aware and physics aware. Another associated and important question remains: how generative models can facilitate our understanding of the 4D world? Again, this is an open question in the community. Here, I will briefly show some kind of examples. One intuitive way is that since the generative model like NERF encodes the global 3D scene geometry, we can integrate it as a prior for the perception model. We demonstrate this idea for the task of a high-definition map, HD map generation in the context of computer driver. So we introduce MWMap, a multi-view fusion framework for HD map generation. By using the scene-level 3D depth prior produced by NERF, our approach produces a globally consistent HD map. So more specifically, we use depth rendering from NERF to produce confidence maps for each bird's eye view BEV feature map. And then these confidence-weighted BEV maps are fused in a region-centric manner to generate globally consistent semantic HD map from the multi-view input. Benefiting from the integration of multi-view data and the global geometry model by NERF, our MV map outperformed previous method by large margins, and it's kind of able to produce a high-quality, globally consistent HD map with multi-view consistency. So this is one example. Another straightforward strategy we can think of is to simply treat the generative model as a data engine and use the synthetic data for data augmentation. So this strategy has been shown great success in tasks like image classification and object detection. Our recent work, H1Div, moved a step further and shows that synthetic data are also helpful for more complicated reinforcement learning tasks. So we introduced a diffusion model, H1Div, to generate full synthetic trajectories based on the given initial state and the task prompt. So as illustrated in this figure, right, given the initial state and the task turn on the line, our synthesizer generates a corresponding trajectory of turning on the line. Intuitively, we can decouple reinforcement learning method into two parts, the replay buffer and the learning algorithm. So we model the original replay buffer with H1Div. In our modified replay buffer, we store the original samples in one replay buffer, and we store the synthesized samples in another replay buffer. And we randomly get samples from both buffers. Since our H1Div only affects the replay buffer without the need for changing the RL learning algorithm, our approach can be applied to all RL methods with a replay buffer. So this is validated by some experimental evaluations. So this result showed that our generated trajectories significantly and consistently accelerate a variety of online RL methods. The right plot shows that, right, so there is kind of noticeable performance gain when introduce our H1Div into the RL methods, such as SAC, RLPD, and parallel. And the left video shows, right, so further the strength of our method, especially in this kind of complicated environment. So we also notice that, right, so the state var PD fails midway and doesn't complete the task. However, with our generator, H1Div, RLPD substantially improve the performance. Okay, this is another example. Not only serving a simple data engine for agents to learn, recently there has also been an increasing interest to directly formulate generative models, especially LMs, as an agent for problem solving. So however, existing work often addresses reasoning, acting, and planning separately, which constrain LM to specific type of a task. Our recent work, language agent tree search, LUTs, unifies reasoning, acting, and planning for LM into a kind of a general prompting framework based on Monte Carlo tree search, and substantially outperforms the prior methods across diverse tasks. So this is the first method that combines reasoning, acting, planning for LM problem solving. As a general prompting framework, it outperforms method from any individual domain. Specifically, right, an internal environment enhances both reasoning and planning by grounding it to the real-world conditions. And the reasoning improves acting by organizing feedback and context. Meanwhile, planning as a search over acting trajectories introduces global decision-making. Notably, our approach is adaptable to reasoning and decision-making tasks by defining a shared state space of actions, thoughts, and observations. So additional advantages are flexible to task or resource constraint, since the dimensions of the tree search can be easily modified. Also, agent is adaptable to conditions on the fly, since the search algorithm will prioritize promising areas of the tree and learn from incorrect solutions. So the key insight of our approach is to adapt Monte Carlo tree search from AlphaZero. Here, we demonstrate the process of our LUTs step by step. So basically, LUTs generates intermediate thinking and acting process towards the final result, and may explore different branches based on any result in the middle. So the process of LUTs searching for answer can be viewed as basically a tree, right? So showing here, where each node is basically a step of thinking and acting. LUTs runs in iterations of the searches for the answer from the root. Okay, play it again. I'm sorry. So basically, LUTs, okay, there's some. Yeah, let me replay it. So basically, LUTs run iteration of the search for the answer from the root. At every node, right? So basically, we can expand possible children in the tree and use a language model to evaluate the possible return value. When we choose the children according to the upper confidence bound in Monte Carlo tree search and repeat the process until we reach the terminal state and get feedback from the environment. If it is not ideal, right, we basically can update the return value with the ground truth feedback on the way back to the root. So we also generate some kind of self-reflection with the language model and add it to the context for the next iteration of the search. So the algorithm ends when the feedback is ideal or the limit of the searching step is reached. So this is a very brief explanation. So experimental results show that our approach outperforms prior method across diverse tasks. So here are some kind of diverse evaluation benchmarks and scenarios. So hotpot QA is kind of interactive question answering task. So we can say LUTs improve both reasoning and acting. Human EVA is basically a programming task, so LUTs enhances the difficult reasoning task. Meanwhile, web shop is kind of web browsing task. Again, LUTs introduces planning to decision-making tasks and improve the performance. Okay, we have shown this kind of sophisticated ways to integrate generative models and discriminative models. One question is there any even simpler way to bridge generative models and discriminative models? We investigate this in the context of multi-model setting with LLM generative model and vision discriminative model. Since the emergence of a language model, right? So they are mostly used as encoders for language or decoder for tokenized output or more structured tasks as what we just discussed. However, our recent work discovers that a single frozen transformer from large language models can be an effective encoder layer for vision tasks. The approach is quite simple. So we directly append a frozen single transformer block from LM, such as the last layer from Llama, after the original encoder layer of vision tasks. So in this figure as an example, right, we show how we integrate this kind of pre-trained language layer with VIT. So first, we use the original patch embedding and self-attention blocks from VIT. We don't change anything. Then we add a frozen LM transformer before the MLP classifier. To align the different feature dimensions, we employ additional 2 linear layers to align the dimensions. Again, our approach is as simple as it. Surprisingly, we found that this kind of strategy is generalizable to various broader range of vision tasks, including 2D image classification, 3D point cloud classification, action recognition in videos, and even non-semantic tasks of motion forecasting. And further, this kind of multi-modality task vision question answering or 3D grounding. So when language is involved, our LM as encoder also benefit this kind of multimodal fusion and improve both 2D and 3D vision language tasks. Across all these tasks, we can see that the simple strategy achieves a significant improvement and consistent improvement. So we're basically trying to analyze and understand why pre-trained transformer in LM without seeing any vision data when training this model actually have this kind of positive effect on vision tokens and vision tasks. So our hypothesis is this kind of information filtering, which is derived from our observation that the feature activation pattern during the process. Specifically, we visual the feature activation in terms of either magnitudes or frequencies. Surprisingly, the models trained with a frozen LM transformer shows emergent tendency of segmenting foreground object, right? So from this illustration, we can see the bird is basically more clearly shown on the activation in either frequency or a magnitude domain. This is surprising, right? Since the segmentation ability only appears on self-supervised VIT like Dino before. Encouraged by this kind of behavior, we formulate our hypothesis as frozen LM benefits from discrimination and amplify the informative tokens as illustrated here. Okay, so as a summary, in this talk, we have shown how we advance generative models to operate in the 4D world that encompasses semantics, geometry, and physics. And we also show how we bridge generative AI and discriminative AI for comprehensive understanding, reasoning, acting, and planning in the 4D world with a lot of different strategies and direction, covering both simple strategies or more sophisticated ones. Again, these are very initial steps towards a big long-term vision. Thank you for your attention. Now I will take more questions.
Hey, Yuzhong.
Yes, I can hear you.
Yeah. Okay, great. So I don't think you were here earlier when I pushed Shenlong and Greg on a question of regularization. So sort of an issue in these density models is you can't really regularize the functional representation in a way that makes sense in terms of 3D. But you may have an answer to that with this multitask claim. Do you want to try and link your multitask story to geometric regularization?
Yeah, so let me go back to that slide. So you are referring to simultaneous synthesis of the RGB and these different sim properties.
Yep.
Yeah. So yeah, I think that's a good point. If we just let's say rely on plain nerve, that would be difficult, right? So if we're just rendering RGB, that would be difficult. But here, I think the positive signal is that if you kind of leverage these different modalities and you explicitly enforce nerve or this kind of MRP to predict these different sim properties due to some kind of relationship, right? So they enforce each other. It looks like this might be one direction. In particular, I think what I showed is in this kind of out of the distribution generalization. So when you train this, somehow it is better regularized. Then if you have some kind of new data set with a different distribution, it still can generate a better kind of clearer RGB synthesized result. So that my guess is internally, right? So they are helping with each other. So because you have to predict both the RGB and these different sim properties, somehow the representation learned is kind of more versatile, right? It sort of encodes a little bit more than just synthesizing RGB or just trying to learn the color and density field. This might be one example. Yeah, the other comment could be there might be some additional information from the pre-trained 2D diffusion model, since they have trained basically on a large amount of data across a lot of classes, a lot of scenarios. It's kind of more generalizable than NERF, I would say, at least in the current version. So somehow we can distill the knowledge from this diffusion model, so we can sort of integrate them to sort of better regularize. That's also in this kind of 3D editing task, the way is trying to bridge the diffusion model and the NERF, right? So they can talk with each other to make the kind of internal representation of NERF is better regularized. Yeah, that's my understanding. But I agree with you, general. This is kind of a very interesting and important direction.
Super, thanks.
Thanks, David.
We could take one more question. Okay, right behind.
Oh, hi, Professor Wang. It's a great talk. I have a question on the performance of your LATS model on diverse tasks. I'm specifically interested in the wipe shop example that you mentioned that your model outperforms the baselines in the decision-making task. So I was wondering do we have a ground truth label for the decision-making tasks, and how do we evaluate in this scenario? Thank you.
Okay, so here we follow the standard benchmark, right? So this is exactly the same information we use compared with all these baselines like React. So the key here is basically we leverage this kind of different information. So we leverage this as mentioned here. So basically, this is to have explicit interaction with external environment, right? Then also we use this kind of reasoning, reflection ability to help search a better, let's say, trajectory or path through the Monte Carlo tree search. So I think that's improvement. Again, I think the approach itself is kind of simple, right? So it's just unifying this and combine this different component, but the performance seems to improve somehow decently. Yeah, that's basically my understanding of this. Is really benefit from this kind of Monte Carlo tree search strategies, like inspired by the AlphaZero. Thanks.
Yeah, thank you.
Okay, well, let's thank Yuxiang again.
Thanks, everyone.